Okay. So, in the previous lecture we discussed the basic concepts of local duality once more, and then we saw how we can take the advantage of local duality in the separable problems, and then we studied cutting plane method, which has a dual sense in its operation. Now, we will discuss the most important method of the dual family, that is augmented Lagrangian method. In if you are following the book optimization book by Kalyan Mahadeb, then keep in mind that augmented Lagrangian method in his book is referred to as the method of multipliers. Any dual method will basically be in a way a method of multipliers. Okay. So, augmented Lagrangian method is also called method of multipliers. Okay. Now, here the Lagrangian itself is augmented with a penalty term. Now, you will recognize that Lagrangian function itself is something augmented, that is, with the objective function, when you add the components lambda transpose H and mu transpose G, then what you get is the Lagrangian, and with that if you add a penalty term for the constraints only, then you get augmented Lagrangian algorithm. While discussing penalty methods, I told you at the end that the penalty method itself is not of great significance for solving optimization problems, but in other methods quite often a penalty term does some invaluable service, and in augmented Lagrangian method you find one such example. So, this is the augmented Lagrangian function. Okay. So, f x plus lambda transpose H plus mu transpose G, that is a Lagrangian, plus this particular penalty function with a penalty parameter C. Now, how does it differ from an ordinary penalty method? In the ordinary penalty method, as we discussed, the penalty parameter C has to be slowly increased, has to be gradually increased to a very high number, that is, perhaps starting from 1 you make it 10, 100, 1000 and so on. Finally, the penalty parameter C may go 10 to the power 6, 7 like that, and that may make the function ill conditioned, that may make the algorithms ill conditioned. In the augmented Lagrangian method, it is a finite C, not indefinitely large C. Ordinary value of penalty parameter something like 4, 5, 10, 15, 12 may be sufficient. Okay. So, the penalty parameter C here is taken just large enough to make the Lagrangian convex. We can, if we can say, to convexify the Lagrangian. So, Lagrangian does not have to be convex at the solution point, at the optimal point x star, but addition of a suitable penalty term may make it convex at the solution point, and that is what this penalty term does in the augmented Lagrangian method. And for that, whatever penalty parameter value is sufficient, that is what we take. We do not take it indefinitely large. A reasonable value is good enough. Okay. So, it thereby it safeguards against any ill conditioning. This is one important point. Now, in what sense it is dual? In the sense that in the main iteration, at every iteration, it is a Lagrange multipliers which are updated. That is, the update of the Lagrange multiplier is the key step in every iteration, such that slowly we approach the correct values lambda star mu star, with which this will be convex not only in the tangent subspace, but in all directions with a finite penalty parameter value C. So, with this combination, one great advantage of augmented Lagrangian method over many other competing methods is that infeasible points, infeasible parts of the domain is absolutely no problem. For example, we have seen problems, we have solved problems with the augmented Lagrangian method in which the domain itself is so complicated that it is very difficult to even suddenly say some point, some solution point which is even feasible. Okay. So, forget about optimality. For example, take this domain, this, 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 now this is the domain. Okay. If this is a feasible domain, then in this plane randomly if you suggest a point, that point is quite possible to be infeasible. Okay. That is what you would expect. Now, this is the domain, this region and perhaps the minimum point lies somewhere here. Okay. You do not know. Okay. And the starting guess point that you suggest might be somewhere here, here, here or wherever, and from there you are supposed to converge to this point. That is going to be tough. Okay. But in augmented Lagrangian method, all these infeasible parts of the domain are very easily navigated through and the minimum point is reached. This is a great advantage compared to a method of the primal family, where to begin with you had to have a feasible point and at every iteration you had to operate always with feasible points only. So, from that point of view, augmented Lagrangian method has a great advantage. Okay. So, what is the method? You select a sufficiently large, but finite, not too large. As I told you 10, 15, 7, 5 quite often is found all right value of a penalty parameter. With that we will stay, we will not increase it later. Select tolerance cutoffs epsilon 1, epsilon 2 for two different purposes, we will see where. So, these are two small positive numbers. Choose the starting point x naught, set the solution iteration count 0 and set all the Lagrange multiplier values as 0 to begin with, because initially you do not know anything. So, put 0 everywhere, all the Lagrange multiplier values. Evaluate the initial augmented Lagrangian according to that formula. Okay. That is Lagrangian plus half C into mod h square sum over all the h's plus sum of the squares of the max of g, max of g 0, okay, g I 0. So, that is the definition, that is the formula for the augmented Lagrangian. By that evaluate T 0 and then from that point you start the loop, keeping lambda k mu k fixed. Initially it is lambda 0 mu 0 0, okay, fixed, and that means only x is variable for the time being, starting from x naught, starting from x 0 in the beginning. Find unconstrained minimum of this, that is for lambda k mu k, for lambda and mu you provide the numbers that are right now sitting. Initially it will be zeros sitting. Okay. So, it is a function of x. You find the unconstrained minimum, okay, by whatever is your favorite method, Cauchy-Newton method, conjugate gradient method, whatever you want. Okay. Just find its minimum with an accuracy epsilon 1. This is where you use one of the tolerance cutoff values on x. Fine. So, converge for x, that is minimize this with respect to x, and therefore, find the next x, x k plus 1 So, now from x k you have found x k plus 1, lambda k mu k are still sitting at the old values. Evaluate t k plus 1, this one. Okay. Now, if this t k plus 1 does not differ much from the earlier t k, that means you have converged, and this convergence, this test you make with the other tolerance number that you have selected. Okay. If it is, if they are too close, two successive augmented Lagrangian values, then you have converged. Basically, x has not changed much last time from compared to the last time. So, then you say that we have converged, we are stopping. Otherwise, what do you do? Otherwise, you will update the Lagrange multiplier values, and the update formula is very simple. Next set of Lagrange multiplier values is the previous set plus the penalty parameter value c into the constraint functions. Okay. Here this and here this, max of 0 and g. And it may happen that some g is active or violated in some iterations, and later it is no more violated, it is no more active. Then the moment some particular constraint becomes active, the corresponding mu is to undergo not only an update, but it will be suddenly made 0, okay, because that constraint is no more active. So, mu will be made 0 if the constraint is now found inactive, and that ends one iteration with the update of the Lagrange multipliers and go back. Now, you will ask, why should it work? Why should this mechanism give me the correct solution slowly over iterations, this kind of iterations? Why should this give you the correct values of the Lagrange multipliers? If the correct values of Lagrange multipliers are found, then you believe that this will give you the correct x star that you know, because this is ordinary unconstrained optimization. So, why should this update work? So, that you can study from two different perspectives. One perspective takes it one subsidiary problem, that is a different problem compared to the original problem given, and tries to pretend that we are solving it by a penalty method. Okay. And when we try to solve this subsidiary problem through penalty method, that amounts to solving the original problem with the help of augmented Lagrangian method itself, and there we see how it works. So, let us see this perspective first. So, the original problem here is to minimize function f x subject to these constraints. Now, in this explanation arguments, I have kept only equality constraints to keep things simple, and inequality constraints I have omitted for the time being. So, the subsidiary problem talks of minimizing not f x, but what would be the Lagrangian, okay, f x plus lambda transpose h x, but subject to these constraints. Now, a little reflection will tell you that if x star is a solution of this problem, then x star is a solution of this problem as well. Okay. So, x star original, x star subsidiary. So, an original solution x star to the original problem is also a solution x star of the subsidiary problem. Okay. As you see that its first order necessary conditions, if they are satisfied, then this fellow's first order necessary conditions also will be satisfied. Okay. Just check grad f plus grad h lambda from here should be 0, right. And for this problem, the grad h lambda star here, okay, grad f plus grad h lambda star should be 0 for this problem, and for this problem grad f plus grad h lambda plus grad h into something, that something happens to be lambda star minus lambda. So, when they add up, you get the same thing, which is 0. Okay. So, first order necessary conditions will be same, except for a change in the Lagrange multiplier. If the original problem has its minimum with Lagrange multiplier lambda star, this new problem will have lambda star minus lambda because of this addition, because it is the same h x that is appearing here and here. Okay. So, original problem is minimize f subject to this constraint, subsidiary problem is minimize f plus lambda transpose h subject to the same constraints. Okay. So, this subsidiary problem has its solution at the same point and Lagrange multiplier differs by this lambda, whatever you have put here. Okay. So, now you say that this subsidiary problem we are going to solve with the help of ordinary penalty formulation, ordinary penalty method, except that the penalty parameter we will not increase indefinitely. So, that will give you this function plus the penalty term, and this happens to be the augmented Lagrangian of the original problem. Okay. So, this is Lagrangian plus this penalty term. Now, we look for the best lambda to define the subsidiary problem, that will be the best subsidiary problem defined. Okay. We notice that if we could somehow get hold of the correct lambda star and we defined the subsidiary problem with the help of the correct lambda star, then this penalty function would be an exact penalty function, in the sense that it would do its job even without C being indefinitely large. Okay. So, if lambda equal to lambda star, then we have got the Lagrangian convex even without making this indefinitely large, but sufficiently large. Okay. So, that is this, that is a Hessian of this T. Now, this Hessian of the T, we claim that it is positive definite for even finite C in all directions. That is, even though the original Lagrangian did not satisfy the convexity requirement, this function does satisfy. Now, how do you do that? How do you check that? You check its positive definiteness in the tangent subspace and in the normal subspace, normal to the tangent subspace. Okay. So, for any vector y, if you evaluate y transpose H L into y, if you evaluate this for any vector y in the tangent subspace and any vector y in the normal subspace, then how does it work? So, if you take a vector y in the tangent subspace, then this is anyway a convex. Okay. And make note that in this part is convex in the tangent subspace. So, for any vector in the tangent subspace, y transpose this whole thing into y, this component of that will be positive and this component will be 0, because in the tangent subspace this is 0. Okay. So, it is in the normal surface that this has something. Now, in the normal surface you will find that if you take this in the normal surface, okay, then there this has no necessity of evaluating to 0. Okay. But this part, it will be C y transpose this whole thing into y. Now, let us write it, C y transpose grad h x star grad h x star transpose y. Okay. And that means basically you notice that this is the transpose of this. Okay. So, that basically means this. Now, if you take y in the normal direction, then this will be non-zero vector, okay? Because a normal vector, a vector normal to the tangent subspace, is essentially a linear combination of the columns of this matrix. Okay. So, this will be a non-zero vector, and the mod square of a non-zero vector is certainly positive. So, y transpose this whole thing into y will come out to be positive for that subspace n in which this fellow has no obligation to be positive. So, that means that is from the necessary conditions of minimality, this component ensures that this behaves as positive definite, where this keeps quiet, this is 0 in those directions, in the tangent directions. In the normal directions, these have no necessity to give you positive eigenvalues. In fact, it can give you negative. Now, whatever negative it is, that will be finite, minus 10, minus 4 or whatever it is. Okay. And this penalty parameter basically needs to be just that much, so that this part with the corresponding penalty parameter is just sufficient to to compensate for the effect of that minus 7, minus 4 whatever. So, if that is the worst from that side is minus 4, then this fellow, as long as it gives you 4.1, you are done. Okay. So, that is how a finite penalty parameter value also works fine. So, this is what is meant by exact penalty function. That is, the penalty function is exact in the sense that even with a finite penalty parameter value, not indefinitely large, it will be doing the job of the penalty function. Okay. Now, so we are looking for the best lambda star, that is best lambda, that is a lambda star to define subsidiary problem. So, that is our job now. So, search the lambda star, the best lambda to define the subsidiary problem, and we note that for every lambda near lambda star, T has a minimum point x lambda near x star, that is the duality. Okay. And at that minimizer, h equal to 0 is satisfied, okay, if lambda is lambda star. So, basically we are looking for the value of lambda for which the minimizer x of lambda satisfies this. This is what we are looking for. Now, this definition basically makes it a system of equations in lambda finally, okay. And this system of equation we want to solve, and the typical iteration for that is this, okay. That is, start with any lambda and use this update formula for updating it, and as you converge you get to the correct values lambda star. Now, the justification for this update formula, this iterative update formula is the following. At kth iteration, optimal Lagrangian multiplier for the subsidiary problem is this, as we have found here, okay, for which the penalty method estimate. Now, here I will remind you to what we discussed in the penalty method. By comparing this grad of the penalized function equal to 0 for an unconstrained optimization methodology with the KKT optimality condition this, we came to the conclusion that a penalty method gives you Lagrange multiplier updates which are like this, okay. And the penalty method that we have, and the penalty function that we have selected for the augmented Lagrangian method gives you delta p del p by del h as simply h x, and similarly del p by del g as simply max of 0 and g x. Okay. So, the penalty method estimate of the Lagrange multiplier gives you this, okay, and this is the estimate of this guy. Okay. So, what will be the estimate of lambda star? For lambda star, the estimate will be the current lambda plus this. and that is the basis of this update formula for the Lagrange multipliers. Now, this is one perspective, one viewpoint by which you can interpret the anatomy, the inside working of the augmented Lagrangian method, in which you pretend to define a subsidiary problem with the objective function replaced with the Lagrangian defined with your prescribed Lagrange multiplier value lambda, and then try to solve it with a penalty method. That is the pretension. Okay. There is another viewpoint, another perspective by which you can interpret the working of the augmented Lagrangian method, and that is a dual viewpoint. Here you pose the other way, that is, for solving this problem, minimize f x subject to h x equal to 0, we are defining a subsidiary problem of minimizing this penalized function, including penalty here, subject to this constraint. Okay. And then say that this subsidiary problem we try to solve by the use of local duality simply. Okay. So, in the definition of the subsidiary problem, we have included the penalty term, and now we are solving it. And if you make a checklist of the previous kind, then you will find that every local minimum, every solution of this optimization problem happens to be a solution of this optimization problem also, because this optimization problem solution means at x star this is 0, h x star is 0 feasibility, and Lagrangian is stationary, that is grad f plus grad h lambda star equal to 0. That will happen here also. So, at x star, if f x star is if the grad f plus this is 0, so you will find grad f plus this fellow's grad. Okay. This fellow's grad is also 0, because h is 0. Okay. So, h is 0, and this fellow's Lagrangian has a 0 gradient, and that will ensure that this fellow's Lagrangian also has a 0 gradient, because this fellow's gradient is 0. You see, this is C grad h into h. Okay. So, that will be 0, because h is 0. Okay. And you will find that the Lagrange multiplier values are also same. So, original is this minimum point, minimum value, and Lagrange multipliers. Subsidiary also has the same things. And now you make an observation that this penalized function is locally convex around x star, even if f x were not. F x did not have any business to be locally convex for sufficiently large, but still finite C. And why? Because this need not be convex in the normal directions, normal to the tangent plane. Okay. But there this will give you the convexity, this component will give you the convexity, as long as C is sufficiently large to compensate for the worst eigenvalue of this. Okay. Now, so since it is locally convex, this objective function or its Lagrangian, so the local duality theory is applicable, and so you apply it. So, construct the Lagrangian and define the dual like this, and recall that the derivative of the dual is simply this. Okay. So, in order to minimize this dual, you will maximize. In order to maximize this, you will need to have this equal to 0, okay, which means this equal to 0. Basically, again you see you are trying to solve this. However, here since it is maximization not minimization, so if you use a first order method, it will not be steepest descent, but it will be steepest ascent. So, for maximizing this, if you want to use a steepest ascent iteration, that will go like the new lambda should be, see this is function of lambda, right. So, the new lambda should be old lambda plus alpha gradient, okay, plus alpha gradient, because it is steepest ascent, not steepest descent. Okay. The steepest descent method said x k plus 1 is equal to x k minus alpha times grad f, right. So, here it is plus alpha times grad phi, and grad phi happens to be h of x of lambda. Okay. So, put that. Now, only new thing that we are doing is that rather than conducting a decent religious line search, we are using the penalty parameter c in place of the line search result alpha, no line search. Why are we doing that? So, to dig that, conduct a little second order analysis, find out the Hessian of the dual, and while studying duality theory, we found the dual Hessian as minus grad h transpose H L plus C times. Actually, there we found H L here, not such a big thing inside. Now, since there is a penalty term, this part comes. Actually, this should be C grad h transpose. Okay. This fellow is inverse. If you thoroughly differentiate the first order derivative, you will get this. Okay. So, minus grad h transpose H L plus C grad h transpose whole inverse into grad h. This is a matrix, this is a symmetric matrix plus C, this is a matrix, this is its transpose inverse, and then this is the original grad h matrix again. Okay. So, since we typically write grad h transpose as A, so this will be written as A, this is A transpose A, this is again A. Okay. So, you get this. And now, if we did not have the penalty term, then this part would be 0, okay. C would be 0, that is putting C equal to 0 is like not having the penalty term. Then the dual would have this Hessian. This is what we derived while studying the duality theory. And now, there is something interesting. Make note of this, minus A symmetric matrix into A transpose, symmetric positive definite matrix. Okay. Not necessarily positive definite in the tangent space. Okay. So, minus A symmetric matrix A transpose. In assignment 1, you had an exercise, this 7th one, which tells you that for n by n symmetric positive definite L and m by n full rank A, this identity has to be proved. Okay. So, what it says is that first of all, this entire product is simply equal to this, okay, and this result is to be used to prove that any eigenvector of this matrix also an eigenvector of this. Okay. Any eigenvector of A L inverse A transpose will be an eigenvector of this also. That is, with inside this inverse with L, if you add this kind of a thing, then any eigenvector of this will remain the eigenvector of the result also. Okay. And how the eigenvalue changes, that is, if the corresponding eigenvalue of this were sigma, then the eigenvalue of this is 1 by C plus 1 by sigma. This is what this exercise asks you to prove. Okay. And this is going to be useful now. As you prove that, you will see that the eigenstructure of this is same, except that every eigenvalue of this will turn out to change in this case to this. That means, whatever are the eigenvalues of this, for corresponding eigenvectors which are eigenvectors of this also, the new eigenvalues of this guy with the penalty term added will be this. And now, if C is sufficiently large, that is large compared to 1 by sigma 1, 1 by sigma 2, 1 by sigma 3 and so on, then what will happen is that all these fellows will be found very close to 1 by C, because in comparison to C, all of these will turn out to be less, each of them will turn out to be less. So, for sufficiently large C, you can simply say that the eigenvalues, all eigenvalues of this matrix will be 1 by C, and that means if all eigenvalues of a matrix are 1 by C, okay, then what? You have the matrix as 1 by C into identity, okay, and that means the dual, the Hessian of this is almost like minus 1 by C into identity. And then if you try to work out the Newton step with that, then you will find new lambda equal to old lambda plus the this minus. So, minus 1 by C I inverse. So, that will be C times I, and this is H. So, that is why identity times H is H, and lambda k plus 1 turns out to be lambda k plus C into H. That is the update formula for the Lagrange multipliers. So, this is in the background that the steepest ascent iteration first order method gives you this structure, and the second order Newton's method also gives you the same structure along with the coefficient value here, which is C. That is why the line search result also in this case would be the same C, and this is how the augmented Lagrangian method is found to work successfully. And I will show you how successfully it works through an example. The problem is to minimize this function over this domain. Okay. Y is less than equal to twice cos x and greater than equal to twice sin x. So, basically two sinusoids with 90-degree phase difference, and between these two the region that is stuck, that is the superset of the domain. The actual domain is defined over and above by an equality constraint, a parabola. Okay. Now, formally stated, it will mean minimize this function subject to h x y, that is equal to x plus y square minus 15 equal to 0, and 2 sin x minus y equal to 0, and y minus 2 cos x equal to 0. Sorry, these are 2 less than equal to 0. So, we started the origin because we did not know any better point, which is the unconstrained minimum point of the actual function. This is certainly 0 at origin, okay, and this is a positive definite function. So, it will never be negative. Okay. So, that is the best starting point that we can think of, and there if we evaluate the constraint functions, you will find that this is not satisfied, okay, and 0, 0. So, this is satisfied at the boundary, okay. Then 0 minus 2. So, this is happily satisfied. So, this is violated badly, this is satisfied at the boundary, and this is satisfied with a margin. Okay. This is inactive constraint. So, only one constraint is really violated, but then you look at the domain. It seems to be a sensible starting point, but it will be knocked out in the first iteration itself, because this is big violation, and see how the domain is. You see, these are the two sinusoids. So far as the two inequality constraints are concerned, the domain is below this and above this. So, that means this segment will be fine, not this, this will be fine, not this, this will be fine, and so on. Over and above that, there is an equality constraint, which means that any shaded region of this plot which falls inside the parabolic curve, that is the domain. That means, domain is from here to here, and then from here to here, and not here to here, this parabolic curve, right. That means, here to here. So, there are two segments of the feasible domain. One is this to this, another is this to this. Everything else is infeasible. Okay. So, outside this, because it is not satisfying the inequality constraints, and anywhere outside this curve is because it is not satisfying the equality constraint. So, now this is the origin, okay, 0 0. Now, in the first iteration of augmented Lagrangian method, crossing through all the infeasible region, it comes here. This is also infeasible, because this does not fall inside this, does not matter. And then slowly over iterations, it goes and settles down here, and that is the solution point. Okay. So, if you blow up this segment, you will see that this long jump is basically this, and then these small crawling is basically this, one iteration, another, and finally, it converges here, which this point satisfies all. Okay. So, it is satisfied this on the boundary, this satisfied with a margin, and this equality constraint also it satisfies. So, this kind of barrier of infeasibility, augmented Lagrangian method can very well overcome on the way. Okay. So, here we complete our dual methods, and in the next lecture we will take up the last family of methods, the Lagrange methods. Okay. Thank you.